Team Floor observed the Chase Center in San Francisco, California via webcam. Observations were done at the end of the day before closing of the site of the particular day of observation. Mortensen Construction and Clark Construction are joint venturing and serve as the general contractors for the Chase Center. The architect on record is Kendall Heaton Associates with office design architects from AE3 Partners. BKF engineers were responsible for civil engineering, land surveying, and planning. The arena will be split into multiple areas: the Plaza District on 3rd Street, waterfront shops, and the Esplanade. Each space will offer guests a different experience. The Plaza District will provide food, beverage, and retail to visitors. The outside of the waterfront area will serve as a large public park which could potentially be home to restaurants, coffee shops, or retail. The Esplanade will connect these spaces and offer space for hanging out, shopping, and dining. The space in total will provide 100,000 square feet of retail, 18,000 arena seats, 3.2 acres of plaza and public space, 950 parking spaces, 300 bike valet spaces, 580 square feet of office and lab space, 24,000 square feet of public plaza facing the water, and will host over 200 events a year.
There is one crew member loading a pallet of 16 OSBs onto a telescopic forklift. This task takes 3 minutes to complete. Once the pallet has been placed on the forklift operator lifts the material and centers it according to the placement of the tear of the black net. This task takes 1 minute to complete. There are 4 laborers waiting on the scaffolding for the OSB to arrive. 2 laborers will unload 1 board at a time. The boards that were taken to a further distance took 2 minutes, whereas the boards that were taken to a closer distance took 30 seconds. Overall, unloading the boards from the telescopic forklift took a total of 10 minutes to complete. Once the boards were unloaded, the forklift operator lowered the forklift back to the ground level. This took 30 seconds. The overall time to complete the cycle was 14 minutes and 30 seconds.
The site conditions during the observation were clear. The weather of 60 degrees Fahrenheit and a wind of 10 miles per hour allowed the work to produce both efficiently and effectively. The footage that was observed was focusing on a facade that is under construction. There is currently OSB being placed on the facade. About 3/4 of the facade is complete. This area of the site has scaffolding and a black net on the perimeter of the building. The scaffolding allows crew members to work safely throughout the day as they unload and place the OSB on the facade. The black net helps during bad weather conditions. For instance, it prevents wind from blowing the OSB away and it shields rain from wetting the material. In addition, the crew members have used a technique with the black net. As seen from the footage, there is a large tear on the net that allows the telescopic forklift to place the OSB for the crew members to unload. On every other floor, there is a similar opening located in the same area. The reason for this is so the telescopic forklift does not have to move locations.
There are 2 major issues in the current operation. Unloaders are not very productive. They are idle for 2.5 minutes of the 14.5-minute cycle. This means that they are only productive 69% of the time. In this operation, they cannot do anything while the forklift is being loaded and while it is rising and lowering to the ground. Additionally, some boards need to be carried long distances, and it takes a long time to unload and carry the OSB boards and to return to the forklift. Half of the OSB boards take 2.5 minutes each to unload compared to the boards that only take the unloaders 30 seconds to load. To combat these problems, we propose solutions that involve adding another telescopic forklift, adding more unloaders, and changing the locations of the forklifts. These changes lead to increased productivity.
Proposal number 1. In this crew breakdown scenario, like the existing operation, there is 1 forklift operator, as well as 1 loader. However, we propose that having 6 unloaders will increase efficiency as opposed to having only 4. The lift in this proposed scenario is also in the same location as the forklift in the existing scenario. This means that once the forklift is unloaded and rises to the level at which the OSB boards need to be unloaded, there is 1 location very near the unloading area that needs 8 of the 16 OSB boards and 1 location that is further away from the unloading location that needs the other 8 of the 16 boards. For this reason, unload carry return time for the 8 of the OSB boards is significantly shorter than the same process for the other 8 OSB boards. In order for one board to be successfully unloaded and carried to the appropriate location, 2 unloaders are needed per board unload carry. In the existing breakdown with just 4 unloaders, the overall time it takes for one cycle to be completed is 14.5 minutes, with 16 boards having been moved to the designated floor. This is because until the OSB boards are completely unloaded, the lift operator, and loader have no choice but to remain idle. Therefore, the goal is to decrease the time that the unloading process takes. Less time unloading means less time the equipment and workers have to be idle. Adding 2 more unloaders would help accomplish this goal without incurring too significant of a cost increase. This proposed operation finishes one cycle in 11.5 minutes, and 16 boards are moved to the upper floor.
This is Proposal 2. In the existing operation, the unloaders have significant idle time. We propose adding a second telescopic forklift in the same location as the first telescopic forklift. While this will be a significant initial cost, we believe that the increased productivity will save money. With both forklifts in the same location, it will be a simple change as the OSB boards will be temporarily stored and loaded in the same area. Additionally, we know the ground and area is a safe and clear space, as this is where the first forklift is located. With the additional boom lift, there will be an additional operator. There will still be 1 loader who assists in the forklift operation and 4 unloaders on the upper floor to unload the OSB boards on the forklift. The unloaders work in pairs to unload the 16 OSB boards off of the first forklift. They move the first 8 OSB boards to nearby areas. Then they move the next 8 to farther areas. Meanwhile, the second forklift lowers and the loader loads the second forklift. The second forklift will rise to the second level right when the first forklift is completely unloaded. The unloaders will work to unload the second forklift in the same manner as the first forklift. Meanwhile, the first forklift lowers to the ground, and the loaders load the first forklift to prepare it for the next cycle. Finally, the first forklift rises to the upper floor right as the unloader finishes unloading the second forklift. The unloaders have no idle time in this proposed operation. The proposed operation finishes one cycle in 20 minutes, and 32 boards are moved in the upper floor.
Proposal 3 is similar to Proposal 2. Again, we propose adding the second telescopic forklift to reduce the idle time of the unloaders. However, this time we propose having the forklifts at different locations around the building. The 2 different locations mean that the OSB boards do not need to be moved as far. The unloaders will have a smaller distance to walk with the boards, decreasing the unloading time significantly. All boards will take 30 seconds to unload, compared to the original operation where some boards took 2 minutes. However, there will be more preparation required. The location of the second forklift will need to be approved and prepared. Additionally, the OSB boards will need to be temporarily stored in both locations of the forklifts. There will be 2 telescopic forklifts, 2 operators, 1 loader, and 4 unloaders. Unloader 1 and 2 work to begin to unload 16 OSB boards from the first forklift. Each board only takes 30 seconds as they only need to move them right next to the forklift. Meanwhile, the loader is loading the second forklift. Once the loader finishes, the second forklift rises and the loader walks over to the first forklift. Unloaders 3 and 4 begin to unload 16 OSB boards from the second forklift. Unloader 1 and 2 finish unloading the first forklift, and the forklift can lower to the ground. The loader loads the first forklift as unloader 3 and 4 still continue to unload the second forklift. Unloaders 3 and 4 finish unloading, and the loader finishes loading the first forklift at about the same time. The second forklift lowers to the ground as the first forklift rises. This proposed operation finishes one cycle in 12.5 minutes, and 32 boards are moved to the upper floor.
For the labor costs, it was necessary to divide the 3 costs into 3 separate sections. We have the equipment, the crew, and the material. Ours means 2016 was utilized to find the daily unit cost per worker and the telescopic forklift to calculate our total cost. Of course, we have to take into consideration the several factors that must be implemented. The first one being the labor factor. The labor factor is a combination between the labor overhead and the CEE index of installation. For the labor overhead, it was necessary to find the bare cost and use the workers' compensation percentage, the average fixed overhead percentage, and the overhead percentage, and then use it to calculate a labor factor that will be multiplied to the bare cost to give us a total wage. Then, of course, we grab the total wage of all the workers all together and divide it by the bare cost to obtain our labor overhead. Then the CEE index factor, we obtain it directly from RS means. For the equipment, we use RS means as well for the CEE index of installation, which is the only factor for equipment. In the case of materials, we also use the CEE index factor for materials from RS means. This will be multiplying our total cost of all the materials that we use per cycle to obtain our final value that has the implementation of the factors. Then we will add the three of them together, the equipment, the crew, and the material, to obtain a final cost. This final cost can then be simplified into a unit cost for facilitation. All the unit costs that were found as daily from all the workers were turned into unit cost per minute to facilitate the calculation, since our cycle times were done in minutes.
For the observed cycle, the unit cost per board was calculated to be $25.02. For proposal number 1, the cost was $25.57. For proposal number 2, the cost was $24.16. And for proposal number 3, the cost was $21.30. In the CAL's calculations, it was determined that proposal number 3 is the best option to implement, since it has the lowest unit cost and had a shorter time per cycle than the observed cycle. Proposal number 3 has 2 telescopic forklifts, which means that equipment and materials around the project site will have to be moved. For example, there are 2 dumpsters next to the structure, which will need to be moved in order for the forklift to get it close enough to the building. It is important to have the materials accessible to save time by allowing equipment to maneuver so that materials can be supplied quickly and efficiently. In order to accomplish this, a worker will be assigned to observe and maintain organization of the materials in this area.